Good morning, everybody. Glad to see so many people interested in talking about getting quantum into the physics and or chemistry classroom. This is really the first of a series of workshops that we would like to conduct with you. So think of this as you're getting just a little bit of professional development right now, but then it's also a commercial for more sessions we would like to conduct with you throughout the fall. I guess I would call it a semester in the high school world. Throughout the fall, from now until December. We'll get more into that commercial later on. Yeah, we're here just to convince you why quantum is a big deal and why you might want to incorporate it into your classroom, which I'm guessing if you're here, you're already potentially interested, so that's a very good thing. Do encourage everybody to scan the QR code to get access to these slides because it has a link where you can join our Microsoft Teams course if you are interested in continuing on. But it also will give you edit access to these slides, and that's how we'll be doing some Q&A with you throughout the presentation. We want you to tell us what you think on these slides. We'll put you in the driver's seat for that. So I'll take a minute for people to get that up on their devices. And if you have a way of getting that link from your cell phone to a laptop you have, then wonderful. If not, there should be a Google Slides app somewhere available for your phone to make the interaction easy. Okay, so while you're getting that up, let me just give you an overview. We're going to introduce ourselves in just a second. It takes an entire slide to do that, so we haven't done it yet. We're going to ask you what comes to your mind when we say quantum, and we're going to ask you what comes to your students' minds, because we're going to find out those are going to be different answers, right? We'll ask the question why there's little or no quantum content in the high school context. I'm sure we all have some ideas of why that is, so we'll look forward to hearing from that. And then we'll talk about why this is important, why quantum needs to be on our students' minds as they're looking forward to their careers. We'll talk about what can we do in this area that's successful in high school, and then we'll give you our pitch. We're going to give you our commercial for the rest of the fall semester. So, my name is Brian. I am mostly a Jacksonville native, Douglas Anderson class of 1999. I have a PhD in computational condensed matter physics, so I went into a quantum career, having seen very little of it in high school. So I am the exception. I want to make that more of the norm. I'm in the physics department over at University of North Florida. I am a reformed condensed matter physicist, now a physics education research person. I've been teaching for 15 years. I've taught quantum in lots of different contexts at the undergraduate level. Good morning. And I've done lots of computational integration. So one of the ways we're going to talk to you about how we can integrate quantum into the high school context is through a computational approach, or through getting students in front of just a few lines of Python code to get them to model the quantum material so that they don't have to encounter the math behind it. Well, so that the math is made a little bit more accessible. I'll let my colleague Taylor introduce herself.
Hi, I'm Terry Galante, and I'm the opposite of Brian in that I'm as far from being a Jacksonville native as you might imagine. I'm actually moving into an apartment today. But I've been working at UNF remotely for the past year. My background is as electrical engineering, specifically computer architecture, but as you can tell, that was back in the 1980s. So I later transitioned into a high school mathematics teaching profession and went on to get my PhD. So I have this wonderful opportunity to collaborate with Brian, bringing my engineering, computer science expertise, computational thinking, and mathematics all together as we try to look at what quantum might look like, even at the physics level, but also even more broadly across all the different STEM disciplines. So super excited to meet all of you and hopefully to be able to work with you.
And Terry and I both started at UNF this time last year. We just met in person an hour ago.
Yeah, an hour ago. He's in my car.
Yes, wonderful trip. And this program we're bringing you is funded by the Hoya Foundation, which means we have money available for this thing. So there's your first little snippet of a conversation there. Okay, so for those of you who just came in, we've got a QR code that'll take you to these slides. And we want to hear from you about what comes to your mind when you hear the word quantum. This is you, this is your reaction. What we'd like for you to do, these slides are editable. So we'd like for you with your mobile device, your laptop, whatever you've got in front of you, to just grab a text cell here and start typing out your answer. If you can add your name at the end of your thought, that'll allow us to trace it back to you. So we'll give you 5 minutes. There are 3 of these pinkish purple slides. So any one of the pinkish purple slides, you just grab a text box, give us a quick answer. What comes to your mind when you think you're quantum? And I'll have a timer here. Okay, well, why don't we let folks continue to type away as much as they would like. Let's take a look at our first slide here. So what comes to your mind when you hear quantum? I hear superposition. That is a 4-syllable word. That is a wonderful word. Anybody want to remind us why that's important in a quantum context?
Is it because of entanglement?
Okay, this is where you get entanglement, right? And that's where the money is in quantum. That's the weird thing. We would love to build it up where your students can at least qualitatively understand entanglement maybe by the end of the unit, right? It's not something I would drop on them the first day, but it is where we want to head because that's the cool kind of stuff that they want to hear about. Computing. Well, I already have a computer. Why would I need quantum in my computer? Anybody know? Okay, first of all, we're going to get smaller, right? So if I can bring quantum stuff into my regular computer, I can make it more efficient. But is there something unique about bringing quantum stuff like entanglement to the computational world? Okay, I can make it more efficient. Does it become fundamentally different though? Oh, we're going to learn about that. We're going to learn about the difference between a classical computer and a quantum computer. I get fixed amount. Yeah, that is literally what quantum means. So when I have to introduce quantum to my students, and by the way, I have to do this in regular physics, right? Because we have this thing called charge that's ultimately built out of electrons and protons, and well, later on quarks, but that charge is quantized. I usually talk to them about it in terms of money. Right? Our money is quantized in units of cents. I can't pay you half of a cent. Well, I could. That's the plot of Office Space. Right? Anybody remember that movie? But, you know, I have to quantize my money, right? Energy, yeah. So this is ultimately what the quantum thing we're looking at is energy. Does anybody teach energy in their classes? I hope you do. So people, you know, I was in a discussion yesterday and people were saying, well, how am I going to add quantum to my class? Well, you're already teaching a lot of the concepts that are related to it. You just say, here's how it works in the regular world and here's how it works in the quantum world, and you kind of transition to that. Let's see. Oh, that came from Asima. Thank you, Asima. So what do we mean by quantum? Well, we mean it's smaller than atoms, right? So we're talking about small sizes. We're talking about low energy. We're talking about low temperature. Basically, whenever our physical properties get small, this is where this weird stuff fits in. Wonderful. And John Maynard wants to talk about quarks. John, where are you? What can you tell us about quarks, John?
So quarks are the building blocks of particles such as protons and neutrons, that they do not make up electrons.
They do not make up electrons. Electrons, we think, are fundamental. I mean, it's a race to the bottom, right? To find what the fundamental thing is. The quarks are the next step down. No, that's great. Oops, I went too far. Sorry. We have energy over here. Oh, somebody mentioned electron spinning. I am so glad. Who mentioned that one? Thank you. I am so glad you mentioned spin. I was in a workshop yesterday with the American Association of Physics Teachers talking about this topic of bringing quantum to the high school world. And everybody agreed the place you need to start is spins. But no one has done a spins first high school curriculum yet. We're going to be the first ones to do that. So we are starting with spin. That'll be wonderful.
And so, Brian, so the beauty of technology is that we're learning as we work with you. And so a few folks were able to comment. So, and so Raj, if you want to give me the rest of your last name, that's great. Talked about bundle. And then we've got small particles from David. Paul talked about non-relativistic behavior of matter and quantum mechanics, and also subatomic. Cool. So thanks for those extra comments that we don't see there.
Yeah, so if you're familiar, the non-relativistic piece, if you're familiar with the rectangle of physics, right, we're in the slow, small corner right now. The fast, small corner, we have to go back to the drawing board, and that's actually where we do get quarks from, is when we go fast and small. Okay, awesome. Let's go to our next one. Let's see. All the math, double exclamation mark. What kind of, anybody who has taken a quantum class recently, what type of math did you have to deal with? There's stats and probability. What else is there?
Oh, there's a lot of matrices.
There's a lot of matrices. Say again?
Calculus.
There's not just calculus, there's multivariable partial differential equations. There's one big one that's missing. Anybody know what it is? Complex numbers?
Yeah.
And that's on the first page of the quantum. Like you open up Griffith's Introduction to Quantum Mechanics, all that is on the first page in the Schrodinger equation. I mean, my God, do students have to complete a math major before they can turn to the first page of a quantum textbook? We're going to talk about that. We're going to talk about how to get around that. We're talking about energy states, so we're not just energy, we have these things called states. Oh, we got my favorite words, the eigens. Right? We get into matrices, we need to start taking their eigenvalues and eigenvectors, and oh, by the way, there's an infinite number of them. No big deal, right? We're going to talk about that.
And Ryan, for some reason, let's see, I think Libera had some things on here about energy, small, atoms, movement, shapes, math. And I really like that presentation because then all of a sudden we start to see, wow, maybe our high school teachers can, our high school students, can talk about these things if we frame them using that kind of vocabulary. So
I was, one of the folks I heard from yesterday was saying they teach third graders quantum mechanics. And they just pull out sporks. And they say, is it a fork or is it a spoon? They say it's both. And they say, oh, so it's in a superimposed state of being a fork and a spoon. And the kids say, yeah. They say, okay, well, how would you represent that mathematically? And the kids come up with some wonderful things. Let's see. Okay, that will be our starting point for the next session, I guess. If you like the slide like that. Okay, cool. Now, I want you to, that's all great. I can't think of anything I would have added to that. But I want to ask another question now. What might come to your students' minds when they hear the word quantum? So you've got your slides open now. Take a couple minutes. Let us know what your students might say. All right, we're going to start in this corner and work our way up because someone has anticipated my punchline. I've got quantitative, meaning more complex stuff. Complex there, I'm sure, is a play on words because it is complicated, and yes, it is literally mathematically complex. Right? Here I've got lots of things. I've got quantify, calculate, movement, invisible. That's pretty cool. That's doing too much. Is that spoken from experience, or is that just a really good guess?
Oh, that's what my kids say to me all the time. Like, this might be that's doing too much.
we were missing the vocal, like the intonation along with the words, so thanks for adding that.
My favorite is when I get told, and when I teach physics too, when we get into circuits. Why are we doing circuits? This is a physics class. What do you think we're going to do? Let's see, we've got that it's hard. I hear vibranium. Oh, that's getting us close. The cat in the box. Hopefully we all know the story about the cat in the box. I had to convince a few people that that was not a literal cat in a literal box with a literal cyanide capsule. It was that it's a thought experiment. Let's see, I hear oh no. And then John has anticipated my punchline. When your students hear quantum, where'd it go? I thought I moved the slide. There we go. Your students are going to say that quantum mechanics saved half the universe from the snap. All right, everybody know who this is? Good, then you guys become well known, right? So Ant-Man gets stuck in the quantum realm, and that turns out to be the secret for time travel, to undo the snap and bring half the universe back to life. Wonderful. So they have the word quantum on the brim. Whether they know at all what it means, because this is a really imaginative movie, and I'm really happy that quantum is on the collective consciousness, but after the word quantum, there's really no science to this, right? That's Mobius strip. That was kind of cool. So it is on your student's brain. So one last little input we'd like for you. Why is there no or little quantum taught in high school? And maybe we transition to some...
Let's do some verbal.
Let's do some verbal. I'm tired of being the one talking. Why do you think we have no or little quantum content in the high school level?
Because there's already very little time for the curriculum you have.
My curriculum's already packed. How am I supposed to cover all this stuff?
It's not a state standard.
It's not in the standard, so I don't got to do it.
Because of the math.
There's a whole lot of, right, that math we just talked about. How am I supposed to do that in the high school level? I can barely do that with college seniors. Yep.
So to actually put an example of when it is in there, the IB physics has a bit in there.
There's a little bit. Tell me, I guess we didn't poll the audience very well. How many of us are teaching physics? How many of us are teaching chemistry? Would the chemistry folks like to tell us about, do they get to do any quantum in their class?
No. Not within the curriculum.
Other than the same orbitals.
Okay, so we do get orbitals in front of me, right? I remember those balloon diagrams in 10th grade. We do get orbitals, and we do get quantum numbers. We do not quantum numbers? Okay. Maybe I'm confusing something. Do we get energy levels?
We do energy.
Okay. Which is ironic because energy levels are easier than orbitals, I feel like. Like, I can draw a ladder really easily, but getting that 3D balloon thing, I don't know about that. So, we know it's possible. Like, it's not cognitively impossible. It's really more a logistical thing of, I don't have room, it's not addressing the standards I'm supposed to address. And so, it's kind of like, well, where's the motivation, right? It's going to be the thing that falls out. Other thoughts, other comments? Yeah.
I think kids love to see the world in a deterministic way when you want to put it in a probabilistic way.
Yeah, we haven't even talked about the change in worldview that comes with this, right? What if the kids go home and say, did you know that my physics teacher tells me that the universe is fundamentally random and chaotic? I mean, how's that going to go over, right?
Or a lot of students say, I can't see it, so that's...
I can't see it, they said, holding their iPhone with the chips inside, right? Right, because we're in this awkward stage in history. Because we know that in 20 years, they're going to need to know some quantum terminology, right? They're not going to need it, not everybody needs a PhD in physics, but they're going to need to be a little bit fluent with it, the same way they're fluent with protons, neutrons, and electrons today, right? But we haven't reached that point yet, but we know we're going there, and so we're trying to get them ready for a world that doesn't quite exist yet, right? And it's hard. It's really hard. Okay, cool. Speaking of which, I inadvertently gave a good transition. So these are some quotes we pulled from some well-known leaders in the STEM industry research field, just about why quantum is important, right? And how it's going to affect these students' lives, more so than it has affected ours, and how it's going to come out in just the type of vocabulary they need, or the type of thing they need to be aware of. Again, not that everybody goes through college and majors in physics or chemistry or whatever, but just that they have that language, right? That they know that that is a thing, and also that they know it's a thing that they can go into if they find it interesting, right? I don't think, no offense to anybody here, I don't think anybody said, oh, I want to go into physics and engineering because I love that inclined plane problem. Right? I'm pretty sure that didn't capture any of those things. So what do people emphasize? Well, they say things like the large tech and research labs working in the pure quantum computing hardware space are looking for people with advanced degrees in key STEM fields like physics, math, and engineering. Right? This is going to be industry needs that we have coming up soon. Train your interdisciplinary perspective. Quantum computing takes expertise from physics, engineering, computer science, and more, right? Nobody is going to study all of those. They're going to study some sliver of it. Well, how does a student know what they want to go study if they don't get a taste for it here and now, right? We're in a very exciting era for quantum computing. And then what do they actually need to learn? Well, they need to learn some linear algebra. We mentioned matrices earlier. Refresh on their trig, particularly the unit circle. We were just talking about that in the car on the way here. And then explore quantum algorithms, right? I don't see any calculus in there. So maybe we can sneak this in at the pre-calculus level, hopefully. Okay, I was going to have folks break into here and read these, but I think we're going to, yeah. This is your first homework, is to grab one of these articles on here. These are written at a high school class accessible language and math formalism, if they use math at all. And so this is some great stuff you can look up just to even introduce as, you know, a project or a report or something for your students, or for yourself to just become familiar with and, you know, talk with your students about. Those are all linked in the slides. We'll have the QR code up again once more, but I think everybody's got it at this point. Yeah, and so this is these are the basics. This is what we are looking to integrate. This is the stuff we're looking to talk to students about. Basically, spin, energy levels, and if we can get to it, wave functions. Which is different than how it's usually presented, right? If you open up Griffiths, it's going to have the wave function ad nauseum, and then say, okay, but these are energy eigenstates, and oh, there's this thing called spin. We should really be doing it the opposite way. Because spin is an incredibly straightforward thing for students to understand, right? It's a coin flip. It's an up or a down, a heads or a tails. They can understand that conceptually. They can even do a smidge of math with it. And then if you take that and build that to energy levels as, okay, you have this 2-state thing, now imagine a 3-state thing, now a 4-state thing, now a 10-state thing. We can bridge up to that and then say, oh, by the way, it represents this probability thing. So this is our approach. This is the commercial. It's also the one with the $sign on it.
So this is the part where you get to come back and work with us again
Yes.
after today.
Yes.
That's what we're trying to sell you on.
Yes. So if you sign up for our program, so we, as far as I know, fingers crossed, you always want to be careful when you say you're the first person to do something. But as far as I know, we are the first high school PD program to do spins first. Everybody else starts with waves. And waves are great. I love waves. But have you asked a high school student about waves lately? They really find it a bit complicated. Because they look at it, it's a function of space and time, and they have to look at all these points. You and I know how to look at it because we're experienced with it. For them, it's a little bit of information overload, I think. This program is going to be adaptable, so you tell us what is working and what is not, and we will adjust it. This is our pilot program. We want to make it work for you. We are not coming in with a cookie cutter. We really want this to be adaptable. And you choose how far to go. Here's what that means. So we've got these 3 stages on here. This fall, we would like to take each of you through basically this intro to spins first quantum mechanics. You have already completed most of Module 0. So if you follow the link at the end of the slides today, you'll be taken to the rest of that first module that's going to have you wrap up, and you will already be 25% of the way through that. Doesn't that sound good? This is worth 30 PD hours for you, and if you complete it at the end of the semester, you get $100. Hooray. Right. Then in the spring, we want folks who are interested in continuing on to either join us in lesson planning and or join us in some advanced modules. That's when there's more PD hours, more money available, more stipend available for that. Then in the late spring, that's where we want to try seeing how this goes in the classroom, and that's where the biggest reward is, because that's the hardest part to do, right? And so we would love to have as many people in each of these phases as possible. We recognize that not everybody is going to go through the entire thing, right? Life will come up, COVID will come up, again, people will get tired, people will have other initiatives they want to pursue, or they'll say, you know what, I got what I needed here, I'm good, that is fine. We will not guilt trip you, we will not egg you on, anything like that. We want as many people in each of these phases as we can.
So Brian, I'm just going to jump in real quick, because I know that's going to come, I believe, later. But this first this is an online professional development. So it is largely self-paced through Google Colab, which you'll actually be learning a little bit of Python. And so a lot of this is new to me as well. So I'm going through the modules as a learner and just really enjoying the opportunity to learn more about how I can expose my students to basic Python concepts. And the different kinds of math that makes these quantum ideas more accessible. So it's largely online, but as you'll see, there'll be some synchronous online meetings, but for the most part, it is yours time, your schedule. So go ahead, Frank.
Yeah, thank you, Terry, for the transition here. So basically, what this first intro sequence is, we want you to complete one module about every 3 weeks. That is self-paced, that you go through at the time that you have available. We will have, or we do have, when you get to the end of the slide, you'll see we have a Microsoft Teams course where you can come on anytime and ask people questions. Right? So when you hit a roadblock and say, I didn't understand how to do step 3, there will be people who have already completed step 3, or there will be people who wrote step 3, and we can give you feedback anytime you need it there. That's the asynchronous part. The synchronous part, once a month, we're going to have Quantum Week. I had to find the Quantum Leap font. I'm very happy to get that up there. But at the end of every month, we're going to have Quantum Week. So Quantum Week starts with the module due on a Monday. Tuesday, we go on and we assess those, and we say, okay, this person, hit all the points here. but the code's a little finicky here, and we give you feedback. It's not a grade, it's just feedback, because, we're all adults and professionals, we don't really need to play things. Wednesday, you'll have the opportunity to review and generate your question, and then Thursday, we think evening, we'll poll you once we get you online. But that's where we'll have a synchronous meeting over Zoom to say, what did everybody think of this module? What can we do differently for the next one? And then we launch into the next cycle in our team. So each of these quantum weeks, we've got the dates listed here. Like I said, we're adaptable. If everybody tells me, no, that's the week of homecoming, something or other, I can't do it, then we just move it. It's that straight, it's that simple. We are at your disposal in that sense. Okay, let me get to our last slide here. So, the next steps, because I think we're just about out of time, you can join our course on Teams. If you click this link here, it will take you to a registration page, because I did find out, Terry, that we can't just drop them in the Teams course. They do have to give us an email address.
Got it.
So if you've got an email with a tied to a Microsoft account, just choose that one. That's the easiest thing to do. If not, it's easy to get set up. That'll be at the registration page. And then you can finish the Module 0 notebook. The link is right here. All the notebooks take place in what's called Google Colab. It's Google's programming documentation environment. It's wonderful. There's an introduction to it when you get there. So just put the link in those steps to walk you through there. So,
And I'll say it's fun. I mean, it's just really fun to take the time to learn something new when you've been away from it for a while. So my last programming before this was Fortran 77, COBOL, if any of you have heard of those.
One,
But
three, four,
just this chance to go really play and explore and learn and think about the possibilities for your students.
Yes.
And the professional development hours come straight from DCPS, so that does count towards your recertification, earning those hours for doing these modules. So.
yeah. So I think that brings us to the end of our time. We have another session, so we're happy to stick around with any questions you have. But thank you all so much for your time. Thank you for your service to our
Dr.
students.
Sinner left some
Okay.
sign-up sheets here that she wanted you all to sign in, so make sure we're here.
Thank you for watching this recording.
And